Assalamualaikum and hello everyone. Today our group will be present about the topic chromatin architecture in gynecological cytology. So before we start, what is chromatin? Chromatin is a macromolecular complex composed of DNA, RNA, and histoprotein found within the nucleus of eukaryotic cells. Its primary function is to efficiently package the genome to fit within the microscopic cellular space while maintaining genomic stability. Now, let's move on to the chromatin organization and compaction. If you stretch out the DNA in just one of your cells, it will be about 6 feet long. To fit inside the microscopic nucleus, the cells utilize chromatin packaging. Next, as you can see in section A of the diagram, from the bottom, the process starts at the 2 nanometer DNA double helix, and DNA wraps around histone proteins to form nucleosomes, looking like beads on string. And next, these beads fold into thicker 300 nanometer fibers, which tightly condense into the classic X-shaped metaphase chromosome during cell division. Now, let's focus on section B of the diagram, which illustrates how chromatin acts as a master switch for our genes. The cells doesn't just pack DNA away forever. It dynamically opens and closes different regions depending on what it needs. On the bottom left, we have euchromatin. This is an open state or active state. An enzyme called histone acetyltransferase or HAT attached acetyl group that is shown as green flag in the diagram to the histones. This causes the structure to relax and open up. Because it loose, the cell machinery can easily get inside to read the DNA and turns genes on. Under microscope, because it is so spread out, euchromatin looks very light and clear. On the right side, look at the bottom right, we have heterochromatin. This is a closed enzyme like DNMT, the black hexagon in the diagram, and HMT, the red triangles in the diagram. Add methyl tags, which cause the chromatin to tightly clump together. Because it is packed so densely, the cell's machinery is completely blocked, turning these genes off. In cytology, because these fibers are meshed together, they absorb a lot of dye and appear as distinct dark staining regions within the nucleus. Crucially, as the center arrow shows, this system is entirely reversible. Using molecular lasers like HDAC, histone deacetylase, and HDM, histone demethylase, the healthy cells can masterfully strip away these tags, flipping chromatin back and forth between euchromatin and heterochromatin to perfectly control its genetic expression. To sum up, active state means the gene is open and being read by the cells to do work like transcription and translation to make proteins for the cells. That's why in the microscopic examination, the chromatin is fine and evenly distributed and the color is smooth. While silent genes means that the gene is locked away and completely turned off. It does not do anything. That's why the chromatin become darker and dense. In cytology, chromatin is incredibly important because it prescribes what we see under the microscope. The way this chromatin is packed determines the shape, size, and staining density of the cell's nucleus, offering a direct window into how the cell is functioning.
Now, let's move on to the nucleolus. First of all, what is the nucleolus? Nucleolus is a dense spherical structure inside the nucleus, and as we can see, it is membraneless. This is because it is held by liquid-liquid phase separation, where proteins and RNA will demix and form a tiny droplet, which what we call as nucleolus. The primary function of the nucleolus is for the synthesis of ribosomal RNA, transcription of ribosomal RNA, and assembly of subunits of the ribosome, where all of these are the most important components in order to make protein to support the cell growth. Have you guys ever wondered why do some cells have inconspicuous nucleoli and cancer cells has prominent one? Let's first look at cells with inconspicuous nucleoli. These usually happen in cells which already differentiated. Because of that, they only has low demand for protein synthesis. Growth signaling pathways are also relatively inactive, so ribosome production is reduced, making nucleolus small and difficult to see. In contrast, cancer cell often has large or prominent nucleoli. This is because cancer cell has high proliferative demand. It requires large amounts of protein to support the continuous growth. Cancer-related signaling pathways such as cMYC, mTOR, AKT, and ERK will activate RNA polymerase I. It also related with inactivation of tumor suppressor such as p53, which strongly increase RNA transcription and ribosome production. As a result, the nucleus becomes larger and more prominent. Finally, nucleolus also act as stress sensor. During cellular stress, such as DNA damage or low oxygen condition, the cell will reduce RNA polymerase I activity to slow ribosome production and conserve the energy. This causes nucleolus to become smaller or even disassembles. And this allows the cell to focus on repair and survival.
Now, let's move on to the factors contributing to fine and evenly distributed chromatin. First, as has been discussed before, hierarchical chromatin organization play an important role for functionality and integrity of entire cellular DNA. Then, move on to the normal chromatin development process. The first contributing factor is chromosome, which control the gene expression by controlling the accessibility of transcription and replication machinery inside the nucleus. Second, epigenetic mark, which is a marker on the chromosome that will alter the chromatin structure into heterochromatin by DNA methylation or into urochromatin by histone acetylation. Epigenetic mark also help to maintain the normal function of proto-oncogenes and tumor suppressor genes, where the alteration will lead to the production of oncogenes. Third, in the normal cell, the proto-oncogene is the gene that wound the chromatin structure and also responsible in controlling the cell growth and cell division. Diagram 11 shows the difference between proto-oncogenes, which is the normal gene, while the oncogene is the cancerous state of the genes. Oncogenes will cause high cell replication and division, leading to high demand of euchromatin to allow the access to more gene replication. The last factor in the formation of normal cell, including chromosome arrangement inside the nucleus. Firstly, inside a nucleus, there are chromosome compartments where chromosomes are organized into two parts. The A compartment, which is for euchromatin, located at the central part, and B compartment, which is for heterochromatin, is at the peripheral part of the nucleus. Secondly, during interphase, the nucleus is in a highly ordered structure where each chromosome occupies a specific territory without mixing with others. Chromatin territories are small and compacted compared to the cancerous cell, which is larger. Thus, chromosomes are well condensed and prevent intermingling between chromosome and compartment switching during extension in telophase. Lastly, the TET function. The normal topological associating domain TET maintains the tumor suppressor gene regulation and also prevent unnecessary interaction between undesired genes. Ultimately, all of the discussed factors in the normal state lead to the formation of vesicular chromatin, or usually described as fine and evenly distributed chromatin. In this state, the chromatin state were in euchromatin structure, which is loosely packed and spread throughout the nucleus.
Now let's focus on the factor that result in coarse chromatin. Imagine your DNA is like a huge library. Every cell has the same book, but not every book should be read. Epigenetic is the system that decides which genes are turned on or off without changing the DNA sequence itself. Today, let's see how abnormal epigenetic change lead to coarse chromatin seen in cancer cells. First, DNA methylation. DNA methylation is the addition of methyl group to cytosine at CpG site by DNA methyltransferases. Think of methylation as a do not disturb sticker on DNA. It prevents certain genes from being read. Normally, most of the genome is methylated because many regions are repetitive DNA. Repetitive DNA is the sequences that are repeated many times. Then we have transposon or jumping genes, which can move around the genome and cause mutation. Methylation keeps these regions silent and protect genome stability. However, promoter of active gene remain unmethylated, allowing transcription factor to bind and gene to be expressed. In cancer, methylation becomes abnormal in two ways. First, promoter hypermethylation add too many methyl groups to tumor suppressor gene. Switching them off, the cell lose control of DNA repair, cell division, and apoptosis. Second, global hypomethylation remove methyl group across the genome. This activates repetitive DNA and transposon, leading to genomic instability, chromosome abnormalities, and abnormal gene expression. So cancer cells gain methylation where they shouldn't and lose it where they need it. Now, let's move on to histone modification. DNA wraps around histone protein to form nucleosome. Histone modification are chemical tag added to histone. For example, acetylation loosens chromatin, making gene active, while loss of acetylation compacts chromatin and silences the gene. In cancer, this balance is disrupted. Some regions become too open, activating oncogene, while others become too condensed, silencing tumor suppressor gene. This creates the uneven chromatin pattern known as coarse chromatin. Another factor is nucleosome remodeling defect. Histone modification and nucleosome remodeling are not the same. Histone modification changes chemical tag on histone, while nucleosome remodeling physically moves nucleosome along the DNA. For example, the SWI/SNF complex uses ATP to slide nucleosome away from a promoter, exposing DNA so that transcription can begin. If SWI/SNF is mutated, nucleosome cannot move properly. DNA remain blocked or exposed in the wrong places, causing uneven chromatin packing and contributing to coarse chromatin.
Next is chromosomal rearrangement. In malignant cell, oncogenes are activated and overexpressed due to genetic alterations. This causes uncontrolled cell proliferation and continuous DNA replication. As DNA replication continues, replication stress occurs leading to DNA damage. Since DNA repair mechanisms are defective in malignant cells, the DNA damage cannot be repaired efficiently and begins to accumulate. The accumulation of DNA damage causes genome instability, which leads to abnormal chromosomal rearrangement. This rearrangement disrupts the normal position of chromosome territories. Some chromosomes move toward the nuclear periphery, while others shift toward the nuclear center, resulting in chromosome territory repositioning. As chromosome territories become disrupted, interchromosomal contacts and intermingling increase because chromosomes are brought close together. Over time, this abnormal intermingling causes the chromatin to become compact and irregular. Under the microscope, this appears as coarse chromatin. So, what's the difference between chromatin clumping and coarse chromatin? In chromatin clumping, during cell division, chromatin compaction is vital to ensure the accurate segregation of chromosomes into daughter cell. Chromosome must be tightly packed to prevent entanglement and errors in distribution. Chromatin condenses further during mitosis, forming visible chromosomes that are easily divided between daughter cells. In coarse chromatin, chromatin form large, irregular clumps within an enlarged nucleus. This appearance is known as coarse chromatin.
So now let's take a good look at the hypochromatic versus hypochromatic. What cause of hypochromatic and hypochromatic color of nucleus under the microscope? For hypochromatic, abnormal DNA content. During malignant transformation, the normal cell cycle checkpoint, like the G1S checkpoint, fail completely. This causes the cell to undergo uncontrolled, rapid replication cycles without dividing its cytoplasm, leading to severe chromosomal abnormalities. gaining extra copies of chromosomes. Under the microscope, hematoxylin acts as a basic dye that relies entirely on a chemical attraction to the negatively charged phosphate groups in the DNA backbone. Because the nuclear membrane have multiplied, the nucleus is forced to bind an excessive amount of dye, creating a uniform, heavily saturated, hyperchromatic appearance. Second, shift to heterochromatin. Cells normally rely on specialized multi-protein engines like the SWI-SNF complex to slide, move, or eject nucleosomes so DNA packaging stays orderly. In cancer, the genes encoding these complexes are frequently mutated or completely lost. Without these engines to properly space out and position the protein spools, the nucleosome become wildly disorganized and lose their structural boundaries, causing the DNA thread to collapse and fold over itself into massive uncontrolled heterochromatin blocks and increase spatial density. If the electrical charges become super dense, pulling in a massive amount of dye make it hyperchromatic. Lastly, cell pyknosis. As a cell enters irreversible injury or early death, the pH of the cell drops sharply. This intense acidity causes the nuclear proteins to denature and causes the entire mass of chromatin to shrink, collapse, and condense into a single tightly packed mass. Because all the DNA has been crushed into an ultra-dense space, the spatial density of its negative charges hits an absolute maximum. It absorbs the hematoxylin so heavily that it turns into a smooth, perfectly round, intensely dark, solid black-purple blob. For hypochromatic, when it shifts to euchromatin, when a cell is actively healing or working hard, enzyme turn off the protein's positive charge, causing the tightly wound DNA to completely uncoil and relax into an open state called euchromatin. The long DNA thread is spread out paper thin across the entire wide volume of the nucleus. Because the DNA is spread so thin, the dye binds very weakly, making the nucleus look incredibly pale, clear, and see-through. Second, karyolysis. When a cell dies permanently, destructive enzymes called endonucleases turn on like a clean-up crew, physically chopping up and dissolving the cell's DNA strands into tiny broken pieces. Because the DNA is shattered and broken down, it completely loses its structure and begins to leak out of the nucleus, fading away into the surrounding cytoplasm. Since the DNA is gone, there is nothing left inside the nucleus to attract or hold onto the purple stain. The staining fades progressively until the nucleus turns into a faint, barely visible outline. Lastly, severe nutritional deficiencies such as a lack of vitamin B12 or folic acid completely impair the cell's ability to synthesize new DNA during replication. This failure results in large, physically bloated cells, dead house pale, underdeveloped, and structurally sparse nuclear chromatin. Because the DNA was never properly built in the first place, it lacks the volume to catch the dye, presenting as a characteristic.
Next, let's take a look at the factors that contribute to thick and irregular nuclear membranes. The nuclear membranes surround and protect the nucleus. It consists of an outer and inner membrane with nuclear pore that allow RNA and protein to move in and out. Beneath the inner membrane is nuclear lamina, a network of protein called lamins. Lamins maintain the nuclear shape and provide mechanical strength, also help to organize the chromatin. There are two main types of lamins, which is A-type lamins and B-type lamins. A-type lamins consist of lamin A and lamin C that provide mechanical stiffness and regulate chromatin, while B-type lamins that consist of lamin B1 and lamin B2 that anchor the nuclear lamina to the inner membrane and attach the heterochromatin to the nuclear peripheral that will maintaining the nuclear stability. A normal nucleus membrane has parent A-type and B-type lamins with intact heterochromatin attachment that will giving it a smooth shape. A thick nuclear membrane has increased lamin and heterochromatin, making the nuclear border appear thicker, while an irregular nuclear membrane has a disrupted lamin network and increased euchromatin, that way reducing the structural support. Now, let's take a look at how irregular nuclear membrane and thick nuclear membrane form. First, irregular nuclear membrane form through lamin dysregulation. Reduced lamin protein caused by genetic mutation or abnormal gene expression weaken the nuclear lamina. At the same time, histone acetylation converts heterochromatin into euchromatin, which bind weakly to the nuclear lamina. The membrane loses support, becoming thin and forming nuclear blips, invagination, and irregular outline. Next, vertical nuclear membrane formed through lamine overexpression. Overreactive lamina A, lamina B1, and lamina B2 genes produce excess lamine proteins, creating a denser lamine network. Histone deacetylation increases heterochromatin, that way strengthening its attachment to the nuclear lamina. Consequently, the nuclear border appears thicker, and the nucleus becomes more rigid and resistant to deformation. In summary, irregular nuclear membrane result from lamine loss and increased euchromatin, whereas thick nuclear membrane result from lamine overexpression and increased heterochromatin.